let's investigate the quartic expansion for the sum of the creation and annihilation operators. The expression that I'm interested in looks like this. We have the creation operator plus the annihilation operator, all raised to the power of 4. In this video, I'm using a shorthand notation for the creation and annihilation operators. They're also known as the raising and lowering operators. Collectively, they're called the ladder operators. With this notation, I aim to visually depict the action of these operators on states. So in this symbol over here, the horizontal line is above because this denotes raising. And in this symbol, the horizontal line is below because this denotes lowering. So this is the creation or raising operator, and this is the annihilation or lowering operator. Now, we can write this in an equivalent form. We can have raise plus lower squared times raise plus lower squared. And then we can expand each of these guys out. So that's going to give us raise plus lower plus raise lower plus lower raise. And then we have another copy of this. We have raise plus lower plus raise lower plus lower raise. So what have we got over here? There are two terms where it's just the same operator repeated twice. That's the same as squaring the operator. We're squaring the raising operator, we're squaring the lowering operator. Then we have two mixed terms. And these mixed terms are not the same because commutativity is not satisfied. If you take the commutator of these operators, you don't get 0. In fact, you get 1 or -1, depending on the order. So we're going to use that property later. But now what I want to do is I want to find all 16 terms that come from this quartic expansion. And I'm going to group these 16 terms in a very convenient way. It's going to allow us to see some interesting patterns. So first, I'm going to write down this term that just has 4 copies of the raising operator. Raise. Now, in the next row, I'm going to write down all terms that consist of 3 copies of the raising operator and 1 copy of the lowering operator. First, I'm going to flip the first position. So we have lower, raise, plus, let's flip the second position, raise, lower, raise. Now let's flip the third position, raise, lower, raise. And now let's flip the fourth position, raise, lower. Now in the next row, I'm going to write all the terms that have an even number of raising and lowering operators. So the number is 2, right? So you have 2 copies of the raising operator and 2 copies of the lowering operator. This row is the most important row because it's going to become very useful when we approximate this quartic expansion. So I'll write that in a special different color. Let's write it in red to distinguish it from the other rows. So we're going to have 6 terms over here. The first term I'm going to write has an alternating pattern. So we have raise, lower. Now we can flip all of these, and that's going to give us lower, raise. And then the next pair is going to consist of 2 pairs, where we have raise, lower, and then lower, raise. So here the operators come in pairs. We have raise squared, lower squared, raise squared. So that's these 2 pairs. So we have a first pair and a second pair, and then finally we have a third pair, and that consists of raise, lower, raise, plus lower, raise, lower. So you can see these guys are also flipped versions of each other. And now let's have a look at the next row. The next row is very similar to this second row over here, except we're going to consider all terms that have 3 copies of the lowering operator and 1 copy of the raising operator. So let's have a look at the first term. We're going to have 1 copy of the raising operator and then 3 lowers, lower, lower, lower. Now we can flip the second one. So if we flip the second one, that's going to give us lower, raise, lower, lower. If we flip the third one, that's going to give us lower, lower, raise, lower. And if we flip the fourth one, that's lower, 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 raise. So this is what we have. And there's one more term, and that final term is all 4 lowers. So we have lower, 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 lower. And this over here is a lower. So I'll write that more neatly. So how many terms do we have in total? We have 16 terms in total. But how many terms do we have in each row? This row has 1 term. This row has 4 terms. This row has 6 terms. This row has 4 terms. And this row has 1 term. So one thing I want to make very clear is the relationship between the raising and lowering operators. The raising and lowering operators are Hermitian conjugates of each other. So I'll write that over here. If we have the raising operator and we take the Hermitian adjoint, the Hermitian conjugate, that's denoted by a dagger, that's the same as the lowering operator. And if we take the lowering operator and do the Hermitian conjugate on it, that gives us this. It gives us the raising operator. So you can see that this notation is very useful for keeping track of which objects are Hermitian conjugates of each other. But if you have the product, it's not as simple as this flipping over here. So if you look at these terms over here, take this term and this term, this term and this term. Each of the individual members of this term are flipped versions of each other, but they're not necessarily Hermitian conjugates of each other. That's because if you have the product, you have to swap the order when you take the Hermitian conjugate. I'll show you an example over here. So if we have, for example, raise lower, and then we take the Hermitian conjugate of that. What we have to do is first consider this second term. We have to flip the order. We have to take this lowering operator, take the Hermitian adjoint, and then we take the raising operator and do the Hermitian adjoint. And that gives us raise lower. So we get the same thing. So this is actually a Hermitian operator because it's equal to its Hermitian adjoint, or it's equal to its Hermitian conjugate. So you can see it's very important that we swap the order when we apply the Hermitian adjoint. And I'll show you another example. If instead we had raise lower, but in an opposite order, so we put the lowering operator first and then the raising operator, and then we took the Hermitian conjugate of that, well, we would have to take this second term and put it here, and then we would take this first term, put it over here, and that would give us lower raise. So you can see that this is also a Hermitian operator. So this is how you would deal with the product of terms. That's how you take the Hermitian conjugate of the product. You always have to swap that order. So it's not quite as simple as just swapping each of the individual terms. So now what I want to look at is these coefficients. Where have we seen these coefficients before? Well, let me draw a little version of Pascal's triangle. So Pascal's triangle looks like this. We have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and 1, 4, 6, 4, 1. These are the coefficients in Pascal's triangle. They are the binomial coefficients. And the binomial coefficients appear over here. And if we had commutativity, if these were elements of some field, like the real numbers or the complex numbers, where commutativity is satisfied, then all of these terms in each of the rows would be equivalent. And we would just have a multiplicity given by the binomial coefficient, which comes from Pascal's triangle. But it is not that simple, because commutativity is not satisfied over here. So what I'm going to do is I'm going to write what happens when we incorporate the canonical commutation relation between these ladder operators. And so what terms are we going to get? I'll write that below. We're going to get, first of all, I'll write these in a more condensed notation. First, we're going to consider this term. So this term from the first row is just the raising operator to the power of 4. Now, this row, I'll write in brackets, is going to give us 4 times the raising operator cubed and then the lowering operator. But it's not just that. Because of the non-commuting nature, we're also going to get 6 copies of the raising operator squared. And later I will derive where this comes from. So this over here has come from the second row. Now let's have a look at the third row. The third row I'm going to write in a different color because it's very special. So the third row has a lot of terms. We have the term that we would expect to see. That is 6 times the raising operator squared and then the lowering operator squared. But there's also 2 other terms. There's a term that has a coefficient of 12 times the raising and then the lowering. And then we also have a constant plus 3. So this is very important. It's going to come up when we have a look at the rotating wave approximation. But for now, let's keep expanding all these other terms. So this has come from the third row. Now let's have a look at this fourth row over here. That fourth row is going to have a term that looks analogous to this. So I'll write that in brackets. We have 4 copies of the raising operator and then the lowering operator raised to the power of 3. But we also have 6 copies of the lowering operator squared. So this is analogous to what we have over here. Over here, the 3 is on the raising operator, and over here, the 3 is on the lowering operator. And you can see that this raising operator has turned into a lowering operator. So this term with a 6 is a consequence of that non-commuting nature. And then finally, from this last row, we have the lowering operator to the power of 4. Now, I want to write this in a far more suggestive notation. So I'll write that below. If we have a look at this, what we're going to get is this I'm going to write in a far more suggestive way. I'm going to write it as 1 times the raising operator raised to the power of 4, and then the lowering operator raised to the power of 0. So it doesn't show up over here, so I'm just going to write it as raised to the power of 0. Then I'll consider this term. We have 4 times this term over here, that is the raising operator to the power of 3, and then we have the lowering operator to the power of 1, so it only appears once. Then I'll consider this term, and I'll write it in red because it's one of those special terms. So this one has a factor of 6, and then we have the raising operator squared, and then the lowering operator squared. And then next, I'll consider this term. This term has a 4, and then it has the raising operator to the power of 1, and then the lowering operator to the power of 3. And then next, we're going to have this term, and that term has a coefficient of 1, but then we have the raising operator appearing 0 times, it doesn't appear over here, and the lowering operator appearing 4 times. And next thing I want to do is I want to add all the miscellaneous terms that don't fit into this pattern. So this is the pattern you would get if you were expanding using Pascal's triangle and the binomial coefficients, where you have 1, 4, 6, 4, 1. And you can see that all of these powers always add up to 4. We have 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3, and 0 plus 4. And you can see that they are ascending and descending. You can see 4, 3, 2, 1, 0, and then 4, 3, 2, 1, 0. So that is the pattern that we expect to see when we do binomial expansions. But now let's collect all the terms that have appeared because of the non-commuting nature of these operators. So we have this term over here. That is 6 times the raising operator squared, and the lowering operator doesn't appear at all, so I'll just write a 0. And then we have this term, which I'll write in red. It's one of those special terms. 12 times the raising operator appears once, and the lowering operator appears once. And then let's have a look at this term over here. We have 6 times the raising operator does not appear, so we have 0, and the lowering operator appears twice. And then finally, we have a constant 3. But this constant 3, we can also write as 3 times the raising operator to the power of 0, and then the lowering operator to the power of 0. And I will close this bracket. So everything in the brackets is a residual consequence of the non-commuting nature. So now what I want to do is I want you to notice what is going on with these powers. So over here, these 3 terms, all the powers add up to 2. we have 2 plus 0, 1 plus 1, and 0 plus 2. And this is the exception over here. It's just 0 plus 0, which is 0. That's because this is a constant term. So there are no creation or annihilation operators appearing in that term. These terms over here are, they do not fit into this pattern. But let's have a look at what happens if you take the difference of all the powers. So I'll write that underneath in green. So we have 4 and 0. What I'm going to do is I'm going to subtract those numbers. I'm going to write that underneath. So over here we get plus 4. Over here, 3 minus 1, that's plus 2. This term is 0. That's very special. Now this term, 1 minus 3, that's minus 2. Over here we get minus 4. What about these terms over here? Here we get plus 2. Here we get 0 again. It's a special term. And then this term is minus 2. And finally, this is also 0. So what do these numbers mean? Well, you can think of the creation and annihilation operators as performing rotations in phase space. If we go back to classical mechanics, in Hamiltonian mechanics, we can think of harmonic oscillators as being circles in phase space. So if we were to graph out position and momentum, we would have these circular trajectories in phase space. And the time evolution would be described by rotations. So that is what these creation and annihilation operators are describing. They're describing rotations. And that translates from Hamiltonian mechanics and classical mechanics to quantum mechanics. And you can think of these guys as being multiplied by complex exponentials, something that has the form of e to the I omega t. And that omega is determined by the difference of these terms. So the difference determines how fast these terms oscillate. You can think of them as rotating. So the terms that have 0 over here, they are non-rotating terms. And you can see they all correspond to the red terms. And where did those red terms come from? They came from this row with 6 terms. So this middle row corresponds to non-rotating terms. All the other terms are rotating, and they're rotating at different rates. And you can see how fast they're rotating. This one is rotating at 4, this one is rotating at 2. This is 4 and 2 times some frequency omega. So the frequency is determined by the difference of those powers. And that is something that's very, very important, because when we do something that's called the rotating wave approximation, we ignore the fast rotating terms. And we only consider the terms that have no rotation, those non-rotating terms. So I'm going to have a separate video where I derive this expression over here, this in red. That deals with the non-rotating terms. And then there's going to be another video that deals with the rotating terms. That's all of these guys and these guys. We don't have to do any derivations for this term and this term. We already have everything because there's only one term that appears here. But for these guys, we want to find out where this 6 comes from. Where do these coefficients that have 6 in them, where do they come from? They come from the commutation relations. So what I want to do below is I want to write something that you might see in first order perturbation theory. This rotating wave approximation is one way of looking at it. Another way of looking at it is this first order perturbation theory. So what I'm going to write is, write this below. Let's say we sandwich this combination of creation plus annihilation to the power of 4. Let's say we sandwich that in between a bra and a ket. So this is a ket and this is a bra. We're sandwiching it in between. And this is how we would evaluate corrections in perturbation theory. So if we were to sandwich these combinations of operators in between these guys, would we get a non-zero contribution from all terms? Well, the answer is no. Some of these terms are just going to give 0. But there are some special terms that are going to be non-zero. Now this comes from the orthonormal nature of these guys. So these are orthonormal states. And that means if you have 2 copies of the same state and you take the inner product, that's going to give you 1. But if you take 2 orthogonal states, it's going to give you 0. So if we act with the raising and lowering operator, we're going to be changing the state. We're going to be either raising it or lowering it. So what we need is to find a balance. We need to find the specific combinations of these operators that bring us back to where we started. So if we raise twice, we have to also lower twice. we can't raise 3 times and then only lower once, because what we're going to get is a different state. Those states are orthogonal, so the inner product is 0. So the only contribution to this is going to come from these terms. And we know that these terms are equivalent to this over here. So I'll write that underneath. That means if we take this sandwich of bras and kets, we can write all of these terms inside. So we have 6 raise squared, lower squared, plus 12 raise lower, plus 3, and then we have the ket. Now, alternatively, we can write this in another form. We can write this as equal to, still have the sandwich. We can repackage these guys, and we can write it in this form. We can have 6 times raise lower squared. I'll write it like this. We have raise lower squared plus raise lower. So that 6 acts on both of these. And then we have that constant 3. There's a lot of brackets over here. It's a bit of a bracket sandwich. And what is this going to give us? Well, this is actually just going to give us 6 times j squared plus j plus 3. So that is the correction. That is the first order perturbation theory correction to the eigenvalues, to these energy eigenvalues. And that's what would happen if we had something like a harmonic oscillator and we wanted to add a quartic term. And that appears when we're dealing with the transmon Hamiltonian. So for the transmon Hamiltonian, we actually do get something of this form, and we do apply this approximation. Now, one way of writing that approximation is stating that it is the rotating wave approximation, in which case we can just say raise plus lower, I'll write that a bit better, raise plus lower to the power of 4, that is approximately equal to all of these terms. So we have 6 times raise lower squared plus raise lower, and then plus 3. So this can be thought of as the rotating wave approximation. But this over here is equivalent. It is first order perturbation theory. Now a question you might have is, how did I jump from this step to this step over here? That actually comes from another video where we'll look at the derivation as how we get to these terms over here. Now, one thing I want to tell you is that if you take the square of the product of these terms, that's not necessarily equal to the product of the squares. So you can see that this is not necessarily equal to this. There are other terms that come up, and those terms consist of raising and lowering operators. So that's just how I jumped from this step to this step. So in those other 2 videos, you're going to see a derivation that deals with the non-rotating terms, which are shown in red, and the rotating terms, which are all the other terms. So this hopefully gives some insight into how I derived the transmon Hamiltonian. You can find all those other videos in the quantum mechanics playlist if you click over here.